So I'd invite you to ponder the following questions. How do we direct current through specific parts of the circuit? How do we adapt voltages to suit situations that we have at hand? And how do we protect sensitive electronic components from excessive current? Hello, I'm Mr. McBrien. This is TEJ3M Resistors. Today we're going to talk about what resistors are, how they're used to limit current and divide voltage, types of resistors, their composition, and some calculations as well regarding resistors. Okay, so to start with, there's a few different kinds of resistors that are available commercially. There are carbon composition resistors that look like the ones on the left, and metal film resistors that are perhaps more common in the TEJ environment and in our classroom. They share a philosophy of communicating to the user quickly what kind of resistor they are, what their target resistance is for which they were manufactured. They tend to use a color code approach. You'll notice if you look at the resistors that are in the metal bin in the classroom that they have colored bands on them. So let's talk about those colored bands for a few seconds. The 3 or 4 band coding is used for 5, 10%, and 20% tolerance resistors. They're the cheap kind that are really just sort of the default to use in a classroom. They're not precision resistors. The first 3 bands are used to denote how much the resistor should have as a resistance, and the 4th denotes the variance from the rated value, how confident the manufacturers are that the resistance you see is the amount they intended. Okay, so how do we interpret them then? The first band is the first digit of the resistance value. The second band is the second digit. And the third band, we can think of this as a decimal place. And all it does is ask you to multiply by a number of zeros. Okay? The 4th band, then, as mentioned before, is the tolerance. So how do we interpret that? Well, first off, we have to examine a resistor, and feel free to go and get a resistor from the metal bin in the classroom if you're in the classroom. So let's look at this resistor that we have on the screen, this cartoon of a resistor though. Our first significant value is a 5. It's a simple lookup table that we'll see in a second. Our second significant value is a 6. And then red is our multiplier value of 100. 2 zeros. Then there's a gap. So the way you can identify which is the 4th band is there's a gap between those first bands and the last one that is the tolerance. And gold gives us a tolerance of 5%. So if we combine all those things together, 5, 6, and 2 zeros is 5,600 ohms, plus or minus 5%. So what that means, by my count, 5% of 5,600 would be 280. So by my count, we can expect that this resistor is going to have something between 5,320 ohms and 5,880 ohms. Feel free to check my math if you wish. We also have precision resistors, and these have a tolerance of 2%, 1%, 0.5%, 0.25%, or the most precise ones, 0.1%. And many of these will use 5 color bands because they have higher accuracy. And in these cases, the first 3 bands indicate the rated resistance value, the 4th band the multiplier, and the 5th one the tolerance. Okay, so I promised you that I would give you some tools to help with interpretation. This is a picture. There are some laminated cards inside the classroom for you to look at, but you can pull this off of the internet extremely easily. And you can see, again, we have our gap between the bands and our precision, or our precision. So we can take the first band and go down and see that yellow is a 4. Take the second band, see that purple is a 7. And the third band, orange, is 3 zeros. And see that this is 47,000 plus or minus 5%. Then our precision resistor down at the bottom has 4 bands, a 5, a 1, a 0, 2 more zeros, plus or minus 1%. Okay, and we will spend some time interpreting the resistors on our sheet, and you can actually take some of the resistors out of the bin and have a look at those. But I invite you to think, are there other ways to determine the resistance of a resistor? So if you think about it, that kind of approach that we just saw for determining the resistance, it's extremely easy to build some software to do a calculation like that. As a matter of fact, it'd probably be a pretty good Turing application to write. So, of course, there are online calculators, so you can go on there and you can use those to check any of the calculations that you do. Any other ways? Anybody think of anything? Well, an obvious thing to do is just measure it. And then we are a little less concerned as well about the precision, because we can measure the resistance of the resistor directly. And so I confess, I don't often use the bands on the resistors. I can recognize a few of them by sight, but usually I just measure them when I'm building my invention. Because of these two approaches, because of applications that we can use, I bet there's an app out there by now that would also help you with this. Because you can measure the resistors, we have covered that concept, and we'll cover it today. But on a test, you will, at the very least, be given the color chart. So please do not try to memorize all of the colors and their interpretations. If I ask you to calculate resistance of a resistor, I will give you a color chart to help you do that. Okay, so there are some other kinds of resistors. Surface mount resistors are little chips that you would typically use on a circuit board. And because they have a little more space on them, they can use alphanumeric labeling instead of colors. And so they'll give you some digits and a letter to help you identify what the resistance is of the chip. And the letter, of course, is the multiplier. Its position indicates the decimal point. So we can see on the left-hand side, the letter is to the right of all of the numbers. And so in this case, it's 22 ohms. In the center case, the letter is in between the two numbers, indicating that there's a decimal between these two numbers. So M represents million or mega. So this is 2.2 mega ohms. And again, on the right-hand side, the K indicates kilo ohms, and it's to the right of all the numbers, indicating that's where the decimal place is. So this is 220 kilo ohms on the right. We won't see many of these kind of resistors in our classroom, but it's good for you to understand how they work. Now, not all resistors have the same resistance at all times. There are some very handy devices that allow us to change their resistance. So, potentiometer is a 3-terminal variable resistor used to divide voltage. A rheostat is a variable resistor, and it controls current. So they're designed differently, of course. So there's our symbols for a rheostat and a potentiometer. Resistors also have, in addition to their nominal resistance, they have a rating for the power that they can handle, the amount of current that you can put through the resistor before it will start to fail. When we have very high current, we need to use specialized resistors that can handle high current, that can handle the power associated with it. And they pretty much always have a physically large surface to allow them to dissipate the heat into the environment. Interestingly, they heat the air around the device, and in some cases can be used to generate heat. So here are some cartoons of some power resistors. Invariably, though, they're going to be large, one way or another. So as I mentioned, the power rating is the maximum amount of power that a resistor can dissipate without being damaged. And the power rating is usually given in the data sheet for a given resistor. It's determined by what it's made from, its size, and its shape. Now, the power rating itself has nothing to do, this is important to understand, has nothing to do with the number of ohms of the resistor. Okay, and the resistors we'll most typically use, their power ratings are typically from 1/8 of a watt to a watt. I think all the ones in our classroom are either 1/4 or 1/2 watt resistors. You want to keep well below that. So make sure your resistor is over specifications so that you don't have any issues in the operation of your device. And relative sizes for what it's worth. Of course, the resistors get bigger as their wattage goes up. Okay, one of the reasons why we'll over-specify our resistors, resistors get excessively hot if we go over their rated power, and they can fail at very inappropriate times. When the current's highest is when we can expect them to fail. They can burn, or we can cook them and the resistance will alter due to heating them up. So anytime you see a resistor that is charred or looks otherwise different than you would expect, you want to remove it from your circuit and check it with an ohm meter. And we'll talk about ohm meters more soon. Okay, we're going to now talk about combining resistors. So you've covered this before back in grade 9, but it's probably a good idea for us to go through it again. Resistors get combined in a circuit in two main ways, in series and in parallel. So the difference in behavior of these circuits is so important, so significant, that we really need to pay very careful attention to which kind of circuit we have and how we view and design our situations associated with these two different kinds of circuits. Resistors in series, for once, we get to use some easy mathematics. So resistors in series, we just add the resistances together because they work together to resist electron flow. So the equation is very simple. The overall resistance is equal to resistance 1 plus resistance 2 plus resistance 3, etc., etc., etc. So if our circuit looks like this, our equation is very, very simple. Resistors in parallel, on the other hand, when we add two resistors to a circuit and we give the system two paths for the electrons to follow, the current distributes between them. Now, electrons are lazy, so what this means is that more current goes through the easier path. But because there's two paths, and each one follows Ohm's law, the overall resistance in our circuit goes down. And this might seem very strange, but we just need to think of it as it's easier to get where we need to go if there are more roads to allow all those cars to travel. So the resistance goes down if we add resistors in parallel. And the equation looks like this. It's not nearly as convenient as the other equation, but if you take the time to do the extension activity for today, you'll see the basis of that math. Essentially, 1 over the overall resistance is equal to 1 over R1 plus 1 over R2 plus 1 over R3, etc. So when we have a circuit that looks like this is the equation that we'll use to calculate the overall resistance. Okay, for your homework then, please do the resistor color worksheet. You don't need to do all of the questions right now. You can save some of them for later if you wish. Do the first 4 questions in each section, please. And do the resistors in series and parallel worksheet as well, please. Now, as an extension, I promised you some additional thinking to do with this problem of parallel resistance. Well, let's take this following circuit here. So this is a standard parallel circuit because there are two paths for the electrons to follow. And what I'd like you to do, I'd like you to consider the potential difference between points A and C, the potential difference between points B and D, and then calculate, based on Ohm's law, the current that you can expect through these two parts of the circuit. And then based on the result, I'd like you to consider the current past point E, and then calculate the resistance of the overall circuit. Finally, I'd like you to compare that result to our equation that we received previously. Okay, so there's a fun problem to work on for those of you who are still comfortable with this material from grade 9. Okay, great. So have a good day, and I look forward to us talking tomorrow.